recording. Perfect. So hello everyone, welcome to a new session of the TBS Colloquia. Today we will have the great pleasure to have Alex Gagliano talk to us about the future, in this case about the future of transient discovery. Alex is a new postdoc at the NSF Institute for AI and Fundamental Interaction in Physics. We are excited to see your presentation, so take it away.
Great. Thanks very much for having me. As Priscilla mentioned, I'm Alex Gagliano. I just started this month as a postdoc in Boston, jointly affiliated with MIT and the Harvard Center for Astrophysics. And today I'm going to be talking about where I think the field is going, at least the field of supernova science and discovery through scalable multimodal analyses. A lot of this is rooted in a paper that we just had accepted called First Impressions, Early Time Classification of Supernovae. And feel free to stop me and ask questions. I will do my best to keep an eye out for a chat, but if someone wants to just shout out a question, that would be great. I would love to have them. All right. So this is the overview of the talk. I'll motivate why we want to study supernovae quickly and what we might learn about them in the first few days of their analysis. And I'll then make a case for why I think contextual information can help us to get there. And that'll lead us naturally into talking about our classifier, which we deemed the first impressions classifier. I'll talk about the architecture and why it's a little bit different from classifiers that have been built to date, and the results from that analysis, and then I'll conclude. Okay. So spectroscopy historically, of course, has informed supernova science from the very beginning. It forms the backbone of our classification taxonomy, and it's maybe no exaggeration to say that a supernova is fully determined by its composition, density profile, and velocity structure, all of which can be probed by a spectroscopy over time. And our discovery rates are increasing. For many events, spectroscopic classification will be the best we can do. But of course, if we want to learn about the nature of the explosion itself and the progenitor star that lost its life, the spectral evolution is what we're really aiming for. The spectral evolution as the photosphere recedes inward and the ejecta of the supernova cool. That spectral evolution probes successively deeper layers of the explosion. And if we wind the clock back and look earlier in the explosion, we can probe the surface composition of an explosion, which is very valuable for understanding how the star that ended its life lived out its final years to centuries. And so just to see how rich in time spectroscopy can be, this is a little video I've made of the spectral sequence of a type 1a supernova. On the right, you can see just how dramatic its evolution can be in the first 30 days and just how much rich information is lost at the level of photometry alone, which you can see on the left. There's the characteristic second bump that we see in type 1a supernovae, which is believed to be an opacity effect. And if we wind back the clock, we can probe the surface of the star that ended its life. That's particularly valuable for core collapse supernovae. So there's this canonical picture that the spectral taxonomy that we've built up, in fact, is a manifestation of a continuum in mass loss degree at the time the explosion takes place. So there are three different example classes of supernovae here: type 2b, which have some hydrogen in their identification spectra, type 1b, which are devoid of hydrogen, and then type 1c, which are devoid of both hydrogen and helium. The thinking is that these distinct classes, in fact, represent a continuum on the side of the progenitor and its mass loss. And if this is truly the case, if it's a one continuum and not discrete progenitor channels toward these types of explosions, we would expect to see traces of elements remaining at the stellar surface to blur the lines between these classifications. We can only do this if we look at the material that is probed by the ejecta in the first couple of days, even the first day of an explosion. This is why we want to get spectroscopy as early as possible. I mentioned that a lot is degenerate at the level of photometry. However, high cadence photometry has taught us a lot in the past few years. So we now believe that high cadence early photometry can reveal diverse signatures, basically of the frozen in state of the progenitor system at the time the explosion took place. So if there's a companion star, then the explosion can interact, and that can cause observable signatures if that interaction is along our line of sight. Potentially, if there's circumstellar material, which we believe to now be surprisingly common in core collapse explosions, then the supernova can interact with this material and lead to observable signatures. And then, to me, the most impressive case is actually detecting the eruptive mass loss episodes of the star before it blows up, and these are eruptive mass loss episodes that have injected that circumstellar material into the environment. So in this way, we can uniquely connect the pre-explosion and post-explosion stages of the star's life. We now think this is a field of science that's going to be completely opened by the Vera Rubin Observatory and its deep, consistent, long baselines in different passbands. I mentioned Rubin Observatory. We're all excited about its discovery rates, which are expected to break exponential scaling. It's thought that we will discover 10 million transient alerts per night and 3 to 4 million bona fide transients across the decadal legacy survey for space and time. This is Elastic, which is a simulation of what we might expect to find in the night sky on a mall-wide projection. Of course, the dates top left are no longer relevant as we've had some COVID-related delays, but the timescales are relevant. So I want you to just look at this mall-wide projection and kind of recognize just how unprecedented this survey will be. Each of those pixels is a different supernova, and it's colored by the class that we might expect to find. So in just the first couple of months, we're going to completely swamp our discovery rates for all supernovae throughout all recorded history before Rubin. It's really remarkable. The point to take away here is that Rubin will be an incredible discovery machine. But of course, at the end of the day, our goal is not to just discover supernovae, it's to learn something about them. It's to learn about the physics of the explosion and connect them to stellar evolution, late stage stellar evolution. And Rubin is not going to do that for us. To do that, we will have to discover things quickly and follow them up with more dedicated science instruments for specialized science goals before the events dim. And that kind of triaging step is what's hard with this data deluge, and it's what a lot of the computational infrastructure we're building up now is in service of, to try and push in this direction. This was the big motivation for Plastic, the photometric LSST astronomical time series classification challenge. Plastic ran in 2019, and it generated 3 million supernovae across the spectrum of time domain phenomena in Vera Rubin passbands. And it has now become practically the gold standard for time domain astrophysics. This is just a small subset of the papers that have come out that have leveraged Plastic data. There are also a few examples where Plastic data has been used outside of astronomy, which I think is really exciting. So there was one paper I found in Quantum ML. I have no idea what that is. There was another paper in, I think, medicine, looking at EKGs or something, and they used Plastic data to train their systems and then did a case of transfer learning. So Plastic, by and large, was an overwhelming success at building up the type of classifiers that can use sparse photometry, multiband photometry, and process many, many alerts. And some of the big hallmarks of success out of this challenge were a series of Gaussian process interpolation techniques that have now come, I would say, become kind of commonplace in the field, and specific architectures of classifiers. So you can see at the bottom table here, the leaders of the classification metrics used some subset of kind of two main groups of classifiers: boosted decision trees and neural nets. Neural nets, of course, have become commonplace throughout our society, not just in time domain, but neural networks have become increasingly the de facto standard for classification. Specifically, recurrent neural networks, this RNN, this third column in neural nets, has become particularly valuable for the specific way that it processes data. So recurrent neural networks I'm showing here, they're similar to a traditional neural network, in which information flows through the network to come up with a final output with a series of neurons or units. Recurrent neural networks are just a little bit different in that information flows through the individual units, but then it can be processed back again in a given unit. And so within a unit, there are a series of gates. This particular unit I'm showing is called a long short-term memory gate unit that has gates to keep information that has long-term significance to the output and forget information that doesn't. And so this is particularly useful for learning correlations in time series datasets, and it's why in the multivariate photometric classification case, it's become such a popular tool. There are a couple of problems with recurrent neural networks as they currently exist in the field. One is ensuring that they still work when you don't have the full light curve information and ensuring that they work on real data. So I mentioned plastic being a rousing success. Many different classifiers has been validated on plastic data, and in plastic, we tried to be as realistic as we could with the data sets, but there will inevitably be a bridge to gap between real data and our simulated samples. And in a lot of cases, we've seen that classifiers that have been validated on plastic data only really suffer in real world settings. On the right, I'm showing RAPID, which is a classifier from Daniel Mutakrishna from 2019. In the top panel is ZTF data, and in the bottom panel is the classification probability, which changes over time as more photometry is ingested. So this is the value of recurrent neural networks. Again, validated only on simulated data. The other big problem is scaling up this type of processing to the 10 million nightly alerts that we're anticipating from Rubin. So we have shown that we can process 3 to 4 million transients, but processing candidate alerts and doing it in such a way that your model is efficient enough to adapt, to retrain, is a significant bottleneck. And actually, there was a paper that came out pretty recently that found that one of their transformer models that performed very well on plastic data, they suffered significant obstacles just loading the model into memory in order to perform the classifications every night on your alerts. So I think this motivates the case of simpler models that are hopefully a little bit more efficient in how they use data and how well they can be quickly spun up and adapted as we learn more about what the Rubin data actually looks like. And I just want to highlight here, there's a class probability that changes over time. And in RAPID, there was the assumption that before you've discovered an event, you have almost zero probability of belonging to any of these supernova classes. And this is reasonable, but it also motivates the question, is that true? Is our assumption that you have a zero probability of seeing any of these transients of a given type before the event occurs? Or can we take advantage of some more informative priors to more quickly come up with a realistic classification? And this, I think, motivates the use of contextual information. Contextual information has been known about in supernova science for a long time. So there have been papers that, for example, will measure the supernova rate in a given galaxy per century, normalized by the luminosity in B-band or K-band, or potentially its stellar mass as inferred from, for example, K-band luminosity. And when you measure out these rates and you split them up by class, what you find is that in the plot on the right, different types of supernovae occur in different types of galaxies. There are correlations here which could lead you to make some prior assumptions about what type of supernova you're going to see in a given galaxy the first second it goes off. And this is all just a proxy for what type of underlying stellar population exists predominantly in that galaxy. If you have an older stellar population, you're probably going to see the explosion of an older type star. And it's the other way with late type galaxies. They have higher rates of star formation. You would expect to find younger explosions, core collapse, supernovae in these cases predominantly. So can we use this type of information for early type classification? Well, this information has been plugged in the past offline. So on the left, in 2013, Foley and Mandel generated a classifier where the probability was solely calculated as an odds ratio over host galaxy properties. So color, luminosity, offset, this was the Lick Observatory supernova sample. And you can see that when you cut off of this probability, you can generate relatively pure samples of type 1a supernovae relative to the core collapse subtypes shown in the color histograms. And then on the right, much more recently, I worked with colleagues to turn this into a random forest classifier on a dataset that we consolidated called GHOST. And we found that we can distinguish between type 1a and type 2 supernovae to just under 70% accuracy using only the properties of the host galaxies. I, again, want to emphasize this is in an offline setting, and the most useful information will be from the supernova itself. So how can we combine all of these pieces, the contextual information and the supernova properties for more informed early classification? Oh, one more thing that I wanted to mention. The use of host galaxy information has motivated an advancement beyond plastic to what's now called elastic, the Extended LSST Astronomical Time Series Classification Challenge. There have been a couple of changes to the classification challenge since plastic. Realistic host galaxy associations are now made for every transient in the catalog. Redshifts are now generated probabilistically and are much more realistic than the lookup tables that were used in plastic. And the transient models, both within our galaxy and extragalactic events, have been made more realistic with feedback from different science teams. And so the Elastic Data Challenge began streaming September 2022. I just want to highlight here that the following month, we reevaluated because it was discovered that problems existed both in our ability to stream that kind of data, to have that high of data throughput, and in brokers' ability to process that much data. And immediately the following month, we decided that we would be running a second Elastic challenge once we worked out all the kinks toward the first one. So I think this kind of speaks to the importance of testing this infrastructure now so that we're ready to do prompt processing on day one of the survey. And if you're interested in how these brokers are doing on Elastic data, I threw the link down below. You can request an account there and find out all of the metrics for all of the classifications are available online. Okay, so this brings us to the first impressions classifier. I made a little video on the left to show our analysis steps for classification. I'm going to probably play it twice because I'm so proud of it. What we do is we take photometry, that is partial phase, and we interpolate it using Gaussian processes. And then onto these matrices, we tack on photometric redshift information and extinction along the line of sight to the transient, and the host galaxy photometry as it exists in the Pan-STARRS catalogs. And then all of that information gets piped into a single layered neural network that is, as I mentioned, a recurrent neural network. So that information flows back through the individual units, and that allows us to get a final classification probability. So the advantage of our particular architecture and analysis, as we've done it, is this is a very small neural network. It's 10% of the number of trainable parameters from RAPID. We use host galaxy photometry in a way that hasn't been done before in classification work. And we use a dual training stage where we first train the network on simulated events, and then we retrain the event, the classifier for a small number of stages on real observed supernovae so that we're able to validate it against real data. And all the details are linked in the paper down below. Our Gaussian process model is extremely flexible. We segment our photometry at each observation, and from the discovery to that observation, we use a Gaussian process interpolation model parameterized by the covariance in both wavelength and time. This is kind of more common now. Kyle Boone, in his 2019 paper as the winner of the Plastic Challenge, pioneered this 2D Gaussian process model. But the fact that we split up the light curves allows us to mimic doing this type of fitting in real time. And the fact that we're learning the covariance in wavelength as well means that you improve all of your fits if you get data in any of your passbands. So just to play that one more time, this is now for simulated LSST data, just so that you can see exactly how this works. And so in early tests, we started looking at elastic data. I'll talk about ZTF data in a bit, but we wanted to test it out using the elastic data that was on hand. And so here are the confusion matrices for the light curve only classifications for 1, 2, 3, 4, 5, 6, 7, 8 different classes. And from 5 days to from discovery to 40 days from discovery, you see that our classification improves. And if we then add in first derived host galaxy properties, we see that at both early and late phases, our classifications dramatically improve. This is really exciting. And in fact, it seems like it fills in the gaps of some classes that are really poorly constrained at early phases, like type 1ax supernovae that are rapidly evolving, but have very strong correlations with their host galaxies that I think are not leveraged as much as they maybe should be in current techniques. So this is really exciting. And the fact that we have these classifications with prior information mean that we can also look at how the classification probability changes over time when the event is discovered. So on the top, we have an elastic light curve, and on the bottom, we have the classification probability for that event. We see that we have a pretty high classification probability of that event as being a type 1a, even before we have any real detections. And then once we have the photometry from the discovery itself, our classification probability jumps up as belonging to a type 1a. So in this case, the host galaxy and the photometry from the event are telling us similar information about what we think that we're looking at. So this is really exciting, but it's all simulated data, so a huge caveat. And how do we actually stress test this type of approach on a more realistic data set? That is what has pushed us to working on ZTF. ZTF in 2019 released its Bright Transient Survey. To date, they have spectroscopically confirmed over 8,000 Northern Hemisphere supernovae. It's a massive survey. And you can see the class breakdown of events they've discovered on the left, obviously avoiding the galactic plane in their discovery fields. On the right, you can see the redshift distribution of the events that have been discovered. Core collapse and type 1a, unsurprisingly, type 1a are brighter. They push a little bit further. But both of these redshift distributions are very, very low. And they're completely incongruous with the redshift distributions that we would get from a survey like LSST. And so Elastic, this framework that we now expanded to associate transients with host galaxies, really broke down when we tried to push it toward these really low redshift samples to generate a simulated data set for training. And I mean, redshift of 0.1, 0.05, it's essentially an edge case for the redshift distribution of simulated supernovae from Elastic. So instead, we had to do things a little bit differently. And we started thinking more broadly about, okay, how do we mimic observed samples and the host galaxy populations that have been discovered to date and do it realistically? We ended up accomplishing that goal with what's called a normalizing flow. So I'll introduce a little bit what a normalizing flow is. Hopefully it's straightforward. I'm sure there are some people in the audience who have heard about them already, but I'll just go through this for the sake of clarity. So our example case is, say we have some finite data set, tabular data, for example, and we want to learn the probability distribution associated with that data set. It's a multivariate probability distribution. And there are a couple of different ways that you could do this. Kernel density estimation is one that historically has been very popular, but kernel density estimates are often not expressive enough to capture the true complexity of the data set that you've obtained. So in this example, the kernel density estimate is in yellow, the true data is underneath in histogram, and then the true distribution is in pink, and you just don't have the kind of flexibility to match the true data distribution. Normalizing flows were introduced to try and resolve some of these limitations. The workaround can be thought of as the following. Instead of learning the P of X distribution directly, we can instead simulate a very simple multivariate distribution, for example, multivariate Gaussian, and then we can learn a transformation between that simple distribution and our more complex data distribution. So this transformation here is G, and what's nice about that is that then we can do something like sampling from P of X, but instead we're sampling from U, generating U samples from this simpler distribution, applying the transformation G onto it, and that transforms us into our data space to generate samples from this more complex distribution. It's really important that this function G is invertible because, before the next slide, this is just an example of how this works. So G, it turns out, is actually a chain of invertible functions that are applied to the latent distribution to transform us finally to our more complex data set. Here it's the 2 moons data set, right? And it's important that G is invertible because if it is invertible, you can play some math games to estimate directly the probability density for a set of observations. So you can generate a posterior, and this allows you to also play games like generating conditional flows conditioned on a given data set and generating the likely values for the other features. So in our case, to generate host galaxy information for the transients that we've simulated, all we do is we take the spectroscopic redshifts of our simulated transients, we take the transient class, and we condition a normalizing flow on those features to predict host galaxy properties trained on the GHOST dataset that I described a little bit earlier. So GHOST is observed data, and by generating this normalizing flow, we can generate realistic pan-stars photometry and photometric redshifts for our simulated events, matching both the correlations with host galaxies and also realistic things like contamination, incorrect association, things like that you would get in any observed catalog, which is really exciting. And that's how we generated pan-stars photometry for the simulated host galaxy. And here are our primary results. So on the top panel, I'm showing a receiver operator characteristic curve for our simulated data set in the primary training stage. And on the bottom, I'm showing it for observed ZTF data in the secondary training stage on day 3. So all light curves that have photometry within the first 3 days of discovery. And so the ROC curve is meant to parameterize how well you're doing in classification. You can see in the legends the area under the ROC curves, which in the limit of perfect classification should be 1. In the limit of completely random guessing, they would be 50%, or that dashed line there. And so the takeaway here is that, unsurprisingly, in the first 3 days on the simulated data, we do really well, but we also do well on the observed data now. There's a degradation in performance, which is to be expected, but within the first 3 days of discovery from ZTF data that has on average a 2-day cadence between observations, we still do better than random at every class that we considered, which is exciting. On the right, we see a comparison plot to one that was released by Pimentel et al. 2022. And so this plot is showing the area under the ROC curves over time as a function of the phase since discovery. And in the first 3 days in that area, I'm highlighting in the red circle, none of the classifiers considered did better than random. They were all at 50%, the baseline estimate. So this shows us that we can incorporate real information that improves the classification just in the first 3 days on real data, which is awesome. And even more exciting, because this is now done in quote unquote real time, as we get more data in from these events, the classification performance improves. So you can see the area under the ROC curves increase across every class as you get more data in. This tells us that probably the early classifier is taking advantage of host galaxy correlations, and at later phases, it's really learning the temporal correlations within the photometry from the explosion itself. So having this kind of multimodality in the classification is really useful to do well at late times and also at earlier times. And it would be useful to look at something like transformers have become pretty common, and they have an element to them that is very valuable called attention. And that allows you to generate an attention score for each data point, which can tell you something about what it's learning in its evolution. We found transforms to do no better on this particular data set, but I might have a later slide showing that, that this has useful properties of telling you what data is most useful for your classification. And we only did this in the 3-class case, but there are other transient classes with even stronger host galaxy correlations that you could easily extend this kind of framework to. And we have those in mind, and we're working on those now. Here is a comparison in the top table, showing our baseline model and every possible classification metric that you could calculate on it. There are lots of different ones that people are interested in for different science cases. What we found was that if we got rid of host galaxy information, if we got rid of our simulated training, or if we got rid of our real data retraining, any of those removals decreases the score of our classifier across every metric. And so this tells us that really all of these pieces are really valuable for doing real-time classification in the way that we're doing it. And just as a hallmark to the Foley and Mendel paper from 2013, they found that their most significant host galaxy feature for classification was morphology. Morphology is not well approximated by host galaxy photometry at the catalog level. And so I believe that incorporating even small postage stamps into a classification framework like this would further improve performance, and that's a step of added complexity that we're trying to think about as well. Right, so I mentioned attention scores and transformers. This Pimentel et al. 2022 paper used a type of attention-based network, and that has the added value that the attention scores you can tack on to the light curves and better understand really where in its evolution do you need to observe the transient for classification. And that's shown in the size of the outlines surrounding the points is the attention score. So I think that's a really valuable extension of this work, and I think could also highlight the trade-off between when you switch from using predominantly host galaxy information to when you start relying on the light curve information itself. Okay. So from this first impressions paper, we have decided, I and my colleagues, that if you're designing an ideal system for real-time transient characterization, ideally it should be highly scalable. It should be as simple and efficient as possible so that you can reload it and retrain it quickly. It should be context aware, taking in as much information as is necessary to do early time classification. And it should be adaptive. So it should not only respond to greater data availability, but now with the rise of active learning, there are systems that are starting to be responsive to specific user feedback. And I think that's a really valuable direction that the field is pushing as well. And I think there's lots of science to be done if we actually pull this off. These are science objectives pulled from the TVS roadmap, the data to software to science with the Rubin Observatory paper from 2022, the white paper, and then the desk science overview in its most recent iteration. And so the things that I'm most excited about with the Rubin Observatory are in-depth studies of fast phenomena, refined theories for the progenitors for some of these explosions, expanding our classification schema with new types and subtypes of events that we've never seen before, and better understanding how the host galaxies of explosive transients are connected to and influence the subsequent explosions. And I would argue, and hopefully I've convinced you as well, that probabilistic context-aware models like the kind I've shown here can help bring us a little bit closer to realizing some of these goals. So I'll end with conclusions there. I think I'm pretty early on time, so lots of time for questions. But there's a QR code for the paper if you'd like to learn more. And so I'll just end by saying that I think contextual information can be very valuable, but models should be adaptive so that they're not constrained by our priors, and that we can actually take advantage of how different Rubin data is going to be from everything we've seen before. And that robust inference models will be essential for many different science cases, but that actually translating these classification probabilities, these real bogus probabilities, into dedicated follow-up pipelines is still kind of an open question and is done manually. I think that's where we're going next. That's what we're going to have to tackle next. And finally, if you are interested in these types of problems in fast inference with sparse light curves and in building infrastructure for the Rubin Observatory and in just solving interesting machine learning questions, then please come join us in the Dark Energy Science Collaborations Machine Learning for Transient Science topical team. I am a co-lead and we would love to have you. All right, thank you very much, and I'll take any questions.
Thank you so much for the very interesting talk.